Okay, so I wanted to go over some more examples of the functional limit. And so to remind ourselves, here's our definition of functional limit. It says that the limit as x approaches c of f of x equals L if and only if the following is true. So for all epsilon bigger than 0, there exists a delta bigger than 0, so that for all x in the delta neighborhood of c, such that x is not equal to c, f of x is in the epsilon neighborhood of L. So that is to say, whenever I have x very close to c, right, then I can make sure that f of x is very close to L. Okay, so we've done a couple examples of this already using our definition as well as some pictures. And so really the purpose of this video is to go over some more examples which are slightly more exotic, just to help reinforce some of the concepts. Okay, so let's consider, say, the following function, f of x. Okay, so this is a function where, of course, the point I care about is this point here when x equals this c value, and it has some particular y value, L. Okay, so you could have told me as calculus students that, of course, the limit as x approaches c is L, because, okay, as we're near it, it's approaching this y value near L, and the singular point at x equals c doesn't matter. Okay, so, I mean, if we were proving this from our definitions, well, as a picture, we care about the epsilon neighborhood around L. Say, maybe I choose this epsilon, which gives me I missed it a little bit, but it gives me an epsilon neighborhood, which gives me a tolerance around the y value of L. Okay, so epsilons are always corresponding to the y values. And so the question is, can I choose a delta sufficiently small around C? So I need a small delta neighborhood around C. In this case, it might be quite small, like this, so that all the x's in this delta neighborhood are, when I map them to their y values, they're trapped within this region. Okay? And so we see in this picture, well, indeed, everything looks like it's getting mapped to maybe this region. Okay? So, yes, everything is getting mapped to something trapped within this epsilon neighborhood, except, of course, for this point itself, right? Right when x equals c, right, we have a problem. But of course, this is showing us precisely why our definition is so crucially dependent on the fact that x is not equal to c, right? So again, for all x in the delta neighborhood of c, when x is not equal to c, it certainly is true that f of x is epsilon close to L. Okay, so this condition that x is not equal to c, when we saw this in our original definition, this was written originally as 0 strictly less than x minus c. Okay, and this would be less than delta as well, okay, to be within the delta neighborhood. Okay, so this condition is really quite important because it allows us to consider cases like this where we have removable discontinuities. Okay, the limit still exists, but mathematically we have to treat for this case, making sure we don't care about what happens when x equals c. Okay. So one more example with a picture to really drive this home. Let's take the example when the limit doesn't exist. Okay, so let me draw some axes. All right, so suppose I'm given the following function here, here, and of course I'm going to talk about this point C, which is here. And suppose I want to check whether or not this L, right, this y value L, does correspond to the limit, right? So we can check whether or not the limit here is equal to L. So again, how do I start checking this? I need to be given first an epsilon neighborhood. So maybe I choose this epsilon neighborhood, which is quite small, around L. And I need to check if I can eventually find a small enough delta around C. So let's see, maybe I take this delta like this. So delta neighborhood. And let's see, where do my points in this neighborhood get mapped? So this point over here gets mapped up here, and everything in this sort of right half of this is getting mapped, I guess, up to here. I don't care about what happens at x equals c, so I'm going to skip this point. And to the left of c, it looks like I'm mapping down here, right? So all of these points are getting mapped over here. So we see that there's some crucial problem with this region. These are all x's which are in the delta neighborhood of c, but f of x is not in the epsilon neighborhood of L. Okay. Put another way, so let me rewrite this in inequality form. This is saying that the distance between x and c is less than delta, but the distance between f of x and L is bigger than or equal to epsilon. Okay? So when we did our proof today of sequential criterion, we had to use the negation of the limit existing, which looked something like this, right? The x and c are very close, but f of x and L are far apart. Okay, so this is really the negation of limits existing. And so in this picture, we see no matter how small I choose my delta, there's always going to be points to the left of c which are down here. Okay, so this construction shows that no matter how small I choose delta, so for all delta sufficiently small, this is always going to fail, right? I'm never going to be able to ensure all of my points f of x are inside the epsilon neighborhood of L. In other words, this is showing that the limit does not exist. Okay, so one last point I'd like to make is just about the sequential criterion. So remember, today we sort of ended class with this discussion of the sequential criterion, which was a way for us to translate this definition, or sorry, this condition of limits existing into a statement about sequences. Okay, so we'd said that the limit as x approaches c of f of x is L if and only if for all sequences in A which converge to c but are never equal to c itself, then the limit of f of those points, f of that sequence, is converging to L. Okay, so I wanted to do here just a quick picture to demonstrate this one more time. So I draw my axes. So I can have a function, let's say like this. And sure, I'll even add a little discontinuity in here. So here's my C, here's my L. And so in order to check that this limit as x approaches c is indeed L, right, you need to think about, here's my real line, right, down here. I'm taking any sequence of points that I'd like which converge to c. So here's my x1, here's my x2, say here's my x3, x4, right, and so on and so on. Any sequence xn which converges to c, I consider what happens when I consider their y values, right, if I plug them into my function. Okay, so x1 gets mapped up to here. This is f of x1. Okay, really it's the y value, right, f of x1. And then x2 gets mapped up here. Okay, so I get an f of x2. Okay, so here's f of x1, the y value. Here's f of x2. F of x3, this point here. So here's f of x3. And so on, right? So you see that the sequence of x values, when I plug them into my function, creates a sequence of y values. Okay? And so the claim is that if I consider all of these x's, and if they're getting very close to c, then I better hope eventually all of the y values get close to L. Okay, and in this picture, we see that if we get closer and closer, right, x4, x5, x6, getting closer and closer to c results in more points getting closer and closer to L. Okay, so indeed in this picture, we have f of xn converges to L. Okay, so this condition of xn converging to c guarantees that f of xn converges to L. Okay, and so if this is true for all sequences, I drew it for a particular sequence here, but if this is true for any sequence I write down, that if it converges to C, then f of that sequence converges to L, then this is another way of checking that a limit exists. Okay. Of course, the negation of this is our condition for divergence, right? That's the last thing we talked about, which is this criterion that if I can find, for example, two sequences both converging to C, but their y values converge to different numbers or don't converge at all, well, then that shows that the limit doesn't exist. Okay? So if there's any questions about this material, please be sure to come talk to me or send me an email, and I'll be happy to talk to you about any clarifications. All right, have a good rest of your week.